because the Q matrices in eight-vertex.
In Liouville's lecture, he was talking a lot. He was asking questions about Q matrices, and he was asking what the definition of a Q matrix was, or a Q operator, or whatever you want to call it. And since I know something about that, or at least I've looked into the question, I volunteered to discuss it with him. So this will not be a field theory talk, because I'm dealing with an eight-vertex model. I'm dealing with a lattice model, but it may shed some light onto what has been discussed as Baxter's Q. So I'm interested in the eight-vertex model. I'll remind you. Oh, first of all, the work I'm doing is discussing is in a series of papers I've done with Klaus Progressius, starting in 2003, and it's summarized in a book I published in January called Advanced Statistical Mechanics. I'm using it in my statistical mechanics class, so in some sense I'm allowed to say that I'm presenting textbook material. Yeah, right. You can buy it on Amazon and the cost is. So, Advanced Statistical Mechanics.
I know that.
Oh, you have it? Ah, my sales are going up. Very good. So, I'm discussing an eight-vertex model. What is an eight-vertex model? Well, there are 8 vertices here. You put these guys on a square lattice, and they have certain kinds of Boltzmann weights, which was found by Baxter ages ago, that if the Boltzmann weights are given by these 4 combinations of theta functions is defined by this, that we're able to define a transfer matrix, and the transfer matrix has certain properties. So what's a transfer matrix? A transfer matrix will depend upon this variable, which I'll call a spectral variable, and it's just a trace of the Boltzmann weights 1, Boltzmann weights 2, that's the Boltzmann weight n, where n is the number of sites, where in a pictorial fashion, I'm just joining these guys together along this axis, and I'm taking the trace over all of the horizontal arrows, and the matrix is a space in a 2 to the n times 2 to the n dimensional space, where these are the variables on the rows, and these are the variables on the columns. We will discover eventually that it makes a difference whether this n, the number of sites, is even or odd. So we have to be a little bit careful about what we're discussing thermodynamic limits and the like, because it makes a marked difference if the number of sites is even or odd. Baxter introduces Q by discussing the famous PQ equation. Let's see if I can do it from memory. Equals some function. We'll define that in a moment. B plus eta Q of B minus 2 eta plus H of B minus eta Q of B plus 2 eta, where this function H is some, I guess, a theta 0, and it's a theta V, and it's a theta H. This has gone down in the literature as the TQ equation, and the question is, what are these operators? And Samson asked the question in particular, what's some sort of abstract meaning of this Q? There are 2 papers that Baxter has written in which he discussed this. Samson referred to the paper of 1972. And there's a second paper of 1973. These are actually markedly different papers, even though, quote, the same equation appears twice. And why they're markedly different is that the paper of 1972 specifically deals with the case where twice some integer times eta, which in some language is called the crossing parameter, is equal to 2m1 times, this is the complete elliptic interval, plus I m2, the complementary interval. Where this is an integer, these are all integers. So these are, if you will, division points on the elliptic curve. I like to call them elliptic roots of unity. If we degenerated this to a trigonometric case, these would be precisely roots of unity. For the 73 paper, these restrictions are slightly different. And we'll see eventually that these things are actually markedly different. So this is an integer, and so we're dealing with only a countable subset of counting parameters. We can't consider this as a continuous parameter. And in order to solve this, or discover this, Baxter makes an ansatz. Makes an ansatz that he wants to find some matrix which will satisfy the following. So since I've now defined all this stuff, which if you've never seen it before, you can't remember it. And if you've seen it before, you think it's boring.
What are the boundary conditions? What are the boundary conditions?
Periodic boundary conditions.
On Q.
In the horizontal direction. I took the trace.
No, this Q operator is a function of V. What are the boundary conditions?
What do you mean by quote, boundary, quote unquote?
If I shift V by K or K prime.
We'll see all of that because I'll give you I'll give explicit formulas. Okay. So
can you just help me with T? What is the argument of the transfer matrix?
U.
T of U.
No, the transfer matrix depends upon. I'm only representing the spectral variable. Okay. It of course also depends upon the Q, and it depends upon the A.
It's just your handwriting I'm having some trouble.
What?
It's just your handwriting I'm having trouble.
Yeah, I know. That's why.
H of V plus U. Do I understand correctly?
Here?
No, in the Baxter equation.
The Baxter equation.
H of V plus U.
H of V plus eta.
Eta.
And that's V minus 2 eta, and V minus eta, and V plus 2.
And the arguments are the same, T of V times Q of V.
Yes.
Yeah. T of V times Q.
Always T of V.
Yeah, Greg is making notes, so it's important.
I'll send you a copy.
Written paper is what I'm just trying to understand in real time.
So, how does Baxter solve the equation, or derive the equation? Well, he starts out by saying, along with this, we need two other conditions. We need the condition that the Q matrix will commute with the transfer matrix, and the Q matrix will commute with itself. And of course, I'm assuming, but I didn't say, that the original property of the transfer matrix is that transfer matrices at two different spectral variables commute. This is the basic equation, which is where those Boltzmann weights came from in the first place. Quantum groups is invented in order to find solutions of that equation. So, Baxter starts out by saying, let's find a matrix such that if it's on the right, I hope you'll allow me to have let's not abbreviate the notation at the moment. So let's find a matrix such that if I have it on the right of T, that it satisfies this. And let's take this matrix Q of R, because this is about the only form we're able to handle, depends upon V, there's some indices for nu and alpha beta. It's a trace of something local, just like the transfer matrix. So we'll start out with something like this.
Again, is something extremely simple. T commutes with Q, so whatever left or right is
No. This is called QR.
it's a different.
It's not called Q. So we're following Baxter's derivation in the 72 period. We start out with the matrix which is defined like this, and it's local. And we can find, so the question is, can we find such a matrix? So this is an L by L matrix, and Baxter finds a matrix which
So
has
the
an
alpha,
element
the
here.
alpha I are up and down, or
What?
something like- Alpha I and beta I are up and down.
Correct. No, these are. It's a matrix, so it goes from here to here. So it's the two indices of the matrix. So Baxter sort of pulls out of the air the following form. You have elements on the diagonal. You have elements on the principal diagonal, and that's everything you have. More specifically, he starts out with something like this, shows that this, that you can find elements which will satisfy this. I can write them down, possibly that's not needed at the moment. These elements actually depend upon a parameter.
This is ansatz for S or for Q?
For S, ansatz for the S. The S is an L by L matrix. This is a trace in an L by L space. To give you a matrix which exists in a 2 to the n by 2 to the n dimensional space. A matrix like this, of course, when plugged into here, will give you identically 0. So you have to have a few more elements. And Baxter just literally pulls out of the air. You put in 2 elements like this. When you do that, this turns out to fix the arbitrary parameter you might have. And for this matrix, he finds it will satisfy this. However, this matrix does not communicate. So we have to do a second computation. Second computation is we'll find something L.
But we don't know at the moment why we wanted to commute with T, yeah? It is just some requirement from nowhere, yeah?
The reason we would like to do that is because in order for the equation to be useful, we want to simultaneously diagonalize everything, turn this into an equation for eigenvalues. Then we're going to, quote, solve the equation by noting that we've constructed something which is an entire function, so I can represent it by its zeros. So if I want to get the zeros of the entire function, I'll let this to be a 0. That will go away. This will give me an equation which looks like, quote, the Bethe-Ansatz equation. This is about the zeros that was discussed by several people in previous plots. So we now construct a second matrix, and now let me abbreviate the notation and drop all these things. You can find the second one of these. So we'll call this R. There's a similar one, S. It's all quite specific with functions because you want to satisfy the equation. But neither one of these satisfies the 2 commutation relations. So in order to get this to hold, we examine the following. And this is where Baxter did not examine quite enough. That we want to do the following. This matrix has 2 symmetries. This matrix is symmetric with the operator S, which is an S sub Z, Z, S, C, Z, these are called spin matrices, and a matrix R, which is X. And it's also symmetric with respect to S. So what I mean by that is that P of S commutes. P of R commutes. Because when we use later, it becomes P of R S commutes.
This S has nothing to do with the S that you use
No,
to
no, no, no.
construct the QR
No,
and QL.
This S has indices, and there's a matrix. This is just a, this counts the parity of the up and down arrows. Baxter makes a statement that his matrices, that since this has the symmetries, that his matrices will have the same symmetries. But there's no reason that that has to be the case. And in fact, we will find that that's not the case, and we'll find the fact that with these constructions, it cannot be the case. In order to prove this, we will prove. Baxter will follow Baxter and try to prove something, but we will be a little more generous than what Baxter was. So this is step one. Step one is to find these constructions. There's three steps we're going to have here. Construct QR and QL. Step two is what I call the interchange relation. So the interchange relation looks like this. L, some variable V1, say what the matrix A is the moment, QR is V2, we suppose it equals QL V2, A, QR V1, where A, Baxter discusses the case where A is equal to 1, that we will discover we would also like to do all of these cases. These all have the property of square root of 1. If we can prove this, and if we have a non-singularity condition, then I can write a Q, which will satisfy a TQ equation, and I'm going to call this Q72 because it's constructed out of the procedure Baxter invented in 1972. It can be written as QR V minus 1 R at some point, which is also equal to A QL minus 1 0 QL A. And we will also find that this will multiply by and both sides. It also holds. From these equations, we will then find that if we have a situation that for there are two matrices, if we have an A1, which equals A2, and we will find that the operator of 1A2 commutes with the this holds that the operator Q commutes with the operator Q72.
Does it imply that there is any time?
We have Q is entire by construction. I haven't given it to you, but this matrix is constructed out of the functions eta and theta. So you know all of the analyticity properties and the quasi-periodicity properties by construction. You don't have to impose it. You know it by the construction. So, am I able to actually prove these two statements for the specific construction given by Baxter? Baxter gives the construction, Baxter discusses the case, and let me recall we have 2L eta equal to 2 N1K plus I and 2K.
Sorry, is it already obvious that it commutes with T?
What?
Is it already obvious that it commutes with T?
The answer is yes. If I use this, it's about a two-step line to show it commutes. So with the definition of the word obvious, which has been used by 95% of the people here, I call it obvious.
What's the role of these torsion points on the elliptic curve? You're just choosing torsion points.
Baxter's paper starts and ends with torsion points. It's all, the construction is all for these torsion points. The point of the torsion points, it turns out, which Baxter did not know and did not comment, is that at the torsion points, if the size of the system is sufficiently large, and particularly if the number of sites is even, there are many degeneracies in the eigenvalue spectrum of the transfer matrix. Therefore, the characterization of the matrix Q as the solution of a second-order difference equation is not good enough to distinguish between the various degenerate subspaces of the transfer matrix T. However, since Baxter doesn't define it that way, he defines a matrix of a certain size. The matrix will have eigenvalues. And what one discovers when one takes this matrix and puts it on the computer, this Q matrix is not degenerate, even though the transfer matrix itself does have lots of degeneracy. Therefore, you are able to count the degeneracies in the eigenvalue spectrum at the division points by use of the Q matrix. That's why I don't like the definition.
So L is your choice. So you can just make any choice of L?
Yes. Baxter wants to argue that since L is my choice, that I can get arbitrarily close to any crossing parameter I want to, and that's why at the end of the day, he takes the formulas he derived for the division points and asserts that's the correct answer for everything. Which for the ground set, for the ground set energy is totally correct. But if you want to ask more refined questions about the nature of the spectrum of the transfer matrix, it misses a variety of things. In some sense, you can say at the division points, the center of the algebra gets larger, and that's the most important. And that's the most important point in construction of any of the RSOS models. They're all taken at division points, and part of the RSOS model is that you take the eight-vertex model at a division point, and you mod out the degeneracies of the system. So Baxter looks at this, and Baxter does the case M2 equal to 0, and he looks at the case N equal to 1, and he proves the interchange relation. That's all very fine. However, in order to actually compute this Q matrix, you have to have the inverse exist. Baxter makes the statement that he checked it on a few low-order cases, and he says it exists. And he assumes it exists everywhere. However, if you just put it on a computer, you will discover that, in fact, it does not exist for all cases. It will exist if M1 is odd. It does not exist if M1 is even. And therefore, cases are missed. Furthermore,
For M2 equals 0, yeah, it arbitrary.
at the moment M2 is equal to 0. I'll tell you very shortly what happens in the general case. Furthermore, the Q matrix has the property that the Q72 matrix has the property that it commutes with one of these operators, but does not commute with both of the operators. And therefore, the fact that the Q matrix does not have the same commutation properties with these operators is what leads to the degeneracy of the spectrum. In fact, there's an explicit statement that the Q matrix has the same commutation properties with the discrete operators as the transfer matrix, but that's not true either. So once we realized that there were certain holes in the argument that Baxter made in 72, we decided to investigate the full case where M2 is not equal to 0. Now, technically, if you want to do that, you'd be better to rewrite the Bolster weights slightly differently, define slightly different data functions, which Baxter does in the 73 paper. But for the purpose of this talk, I won't bore you with putting those formulas on the board. So we can go through exactly the same procedure, and we'll find the following, which I can summarize in this paper. So, I want to summarize the values of A remember that it's 1 R, RS, RX, or RS for which interchange holds. And curiously enough, for reasons I do not understand, it depends upon the parity of M1 and M2. There are 4 cases that M1 is odd, M2 is even. This quote is the generalization of the case that Baxter originally did. M1 can be odd, M2 can be odd. M1 can be even, M2 can be odd, and they can both be even. And let's say which of the A's it commutes with. You find in the case that Baxter did, commutes with those two, does not commute with them, does not interchange with those two.
Always commutes with 2 of them.
Always commutes with, no, it always commutes with at least 2. But even in the case it commutes with all 4. This is a commutation relation that Baxter asserted held for this case. We can then check non-singularity. In these 3 cases, it's non-singular. This case, however, is singular. Therefore, even though in the even case the interchange holds for all 4 of the discrete operators, since it's not singular, we cannot compute a Q72 because the inverse doesn't exist. So that's very curious. There's now one case where the original construction of Baxter does not work. Is there a way to patch that up? Well, for quite a while, we didn't know there was a way to patch it up. But a couple of years ago, Fabricius, my co-author, and independently Rowan, discovered that since Baxter just pulled his matrices SR and SL out of the hat, maybe you can pull something else out of the hat. So now we'll go back to a matrix SR. We have the off-diagonal elements. You can't really get away from those. Baxter discovered put elements here. Rowan and Fabricius and Rowan said, what happens if I put an element here? So now we have sort of a cyclic matrix. In fact, this will indeed satisfy the equation T QR, HQR plus HQR, and correspondingly with QL. And in fact, I made an offhand comment that in Baxter's original discussion, that the elements here depended upon a parameter, and that Baxter chose, once he chose these elements, he chose a parameter. These things also depend upon a parameter, we call it P, and in fact, in order to satisfy this equation, it satisfies it for all values of this parameter T. On the other hand, let's note a certain property of this. If n is odd, that's the number of sites. If n is odd, then if we plug into Q is the trace of SSSS, we had better have an even number of sites in order that we get elements on the diagonal. If n is odd, this is identically 0. So, in order to get something non-zero, I'm now restricting myself to the case that n is even. We can now attempt to replay the same game. We have an extra parameter at our disposal. And we look at the interchange relations. And now we've discovered that we can make the interchange relations hold if we make a specific choice for the parameter t. And it turns out there are two possible choices for this extra parameter. Well, first give the choice when t is equal to some integer times eta. And we'll have another one of these guys. Now, both M1 and M2 are even, so we now discover there are extra parity conditions that depend if M is congruent to 0 or 2 mod 4. Again, why such a condition should come up, I have no idea. So I'll let 0 or 2 be what the congruence is, and we have another one of these tables. And if I use the case that my extra parameter is here, turns out that I'm really being a little overly pedantic, because in this case, it works for all cases. And we find that result is always non-singular. However, it turns out there's also a second choice. We can choose if my extra parameter t is eta times n plus f. And now we get a different table. I will redo this on the mod 4 and do the same thing. And now we find a table like this. Yes, yes, no, no. Yes, yes, yes,
understand something here. Once you've found the case that works, that satisfies your three conditions, so you can construct this Q, why do you want to, I mean, do you want to have different Qs?
Yes,
Matrices?
because that's going to give you more information about the degeneracy spectrum of the transfer matrix.
I see. So one Q that works doesn't suffice to give it.
We will see that there are cases here where you get different commutation relations with the two discrete operators.
But there have to be two solutions anyway.
What do you mean?
There have to be two Qs, in a sense.
This is different. This is not in that sense. And you will remember that actually, if we are dealing with Baxter's literal problem, that you don't have two solutions which satisfy the quasi-periodicity condition. It is like differential equations with integer differences of exponents where you get a logarithmic solution. That's why Baxter never, quote, discusses the second solution, because the second solution doesn't satisfy the right quasi-periodicity conditions. Bosanoff has a lovely discussion of this in one of his papers. And again, in the case where, this case here, where it commutes with everybody, it is non-singular. It is singular. The rest of them are non-singular. So we now have a variety of different Q matrices. So I can't quite uniquely tell you what the operator, there is no, quote, unique definition of a Q matrix, at least at division points, because we found several different ones which are generally different. Some of these are similar to solutions we've already found, but the ones which have different commutation relations cannot possibly be similar to the ones which have already been found.
Yeah, but I really understand very little of this. Given a Q matrix, you can find the ground state energy, right? And you can also find more things. Other eigenvalues of the transfer matrix.
You can find them all.
So
they all satisfy.
What's the point of having more than one Q matrix? I mean, if you've got one, then you can get the spectrum of the transfer matrix. Aren't you happy at that point?
I want to point out, there is one case still we don't have a Q matrix. We don't have a Q matrix in the case that n is odd, and both of these guys are even. This is a very interesting case. This is probably the most interesting case. Why is this the most interesting case? Because this corresponds to the case first discussed by Stroganoff in his famous paper, The Importance of Being Odd. It corresponds to if I degenerate this to the XXZ model, corresponds to one of the cases is where the parameter delta is equal to -0.5. And in that case, he gets wonderful combinatorial problems, wonderful combinatorial solutions. However, we don't have a Q matrix. So I can even less answer the question, what is the definition of a Q matrix? Because there is this case where at the moment we don't have one. Now, there really ought to be one, but we don't have one. So there's clearly something slightly missing here.
Okay, that partially answers the question, but not completely, because I mean, in the cases where you do have a Q matrix and n is even, why try and find another one?
This is a compensation. Yeah.
No, I didn't try to find it, okay? What I was attempting to do, what I'm attempting to do is I have a parameter. I want to find all values of the parameter which satisfy things.
It looks like
And I get Q matrices which have different commutation properties with the discrete operator. So they're different.
Right.
So in some cases, so depending upon which one you use, you will see different properties of the transfer matrix itself. This will tell you that if there are two different Q matrices which have different commutation properties with respect to the discrete operators, that's going to change the degeneracy structure of the transfer matrix.
Oh.
What does it mean? So let's go back now. What does it mean that we have a Q matrix, we have a TQ equation, and there's a degeneracy, and yet the Q matrices are different? What's going on? So we have TQ is equal to H to H. Well, if these are degenerate, there has to be some, but there's some difference in these eigenvalues. But we'll now diagonalize everything, so I can be speaking about eigenvalues. The other way that can happen, this dependent upon V, this dependent upon V minus 2 eta, dependent upon V plus 2 eta. Since these are quasi-periodic functions, they can be represented as some product over there, since the size of the system is n, so they're n zeros. So we'll let this be the number of zeros. Goes 1 to n. Parameterize it in terms of these zeros. The eigenvalues can be different for the same eigenvalue here if there are some of these zeros which will cancel out in this equation. So if there is a periodic string of zeros, so if V can be equal to some V0 plus 2n to eta, V0 plus 4 eta, on out to the maximum number, which is given by the division points, that they'll be periodic, they'll all cancel out of this. So for one t, you're able to get several different ones of these q's, because they differ by these things which are called complete L strings. How do we see the degeneracy? Well, let's now write what the fundamental region of these various theta functions is. The original theta functions are defined from 0 to 2k and 0 to 2 on theta. However, this is not the quasi-periodicity structure of the transfer matrix. Transfer matrix depends upon this function h, which was the product of theta and theta. So if you look at what that is, this is the same thing as an h function with half the, well, you've essentially done a Langdon transformation. The quasi-periodicity of this is exactly half the quasi-periodicity of the original function with the Boltzmann. So if you have one of these strings which lies here, and you apply one of these symmetry operators, that will give you a corresponding string which lies up here. So if you have so for every one of these sets of zeros, which goes into the eigenvalues, if you have a complete string by applying the symmetry operation, which Q does not commute with, you will get something different. The transfer matrix, you didn't get anything different, but for Q you do get something different. You get something which is translated into the other half of this period. So if I have NL, number of these strings, I can apply the symmetry operation to each one of these strings separately. So I will end up with 2 to the NL possible different eigenvalues for Q, which correspond to the same eigenvalue for T. So that's a way to count the various degenerate states of T in terms of these different eigenvalues of Q. So it's not at all clear what a generic definition of a Q matrix is. Baxter has a second paper, has a paper in 73. It finds another Q matrix. Only in this case, n is forced to be even. And the Q matrix he finds here does indeed commute with all of the operators, with both R and S. So the Q matrix he finds in the 73 paper is incapable of resolving the different degeneracies.
Oh, so for this one there is no degeneracy. They don't factor.
Well, correct. He will have, and he comments in his paper, he will have these strings, all right, but his strings are involved in the half planes at once, so the symmetry operation turns one into the other.
The key point was to find that something which commutes with only symmetry operation.
No, the key point is to find a Q matrix which does not commute with one of the symmetry operators. If it commuted with the same symmetry operators which the T matrix commuted with, you wouldn't learn anything about the degeneracy structure. And in fact, Baxter's original computation of 72, if he hadn't made the mistake, he would have discovered that in fact his Q matrix did not commute with the reflection operator R, and therefore he would have seen a degeneracy structure. So this is what I wanted to sort of answer you in your question about, is there an abstract definition to the operator Q?
The answer is basically that for odd one, for odd, there is none.
For odd and the case that both of those m's are even, we do not have a Q matrix yet. There must be a Q matrix, but at least I think there has to be. Okay. I believe there's a Q matrix, but I do not know how to construct it. So since I can't construct a Q matrix for a case where I think it ought to exist, I certainly don't have an abstract definition. So with that, I'll let you go. 10 minutes.
So what about the non-rational case? You not like the torsion point?
I'm actually unwell. The person to answer that question is Leon. Okay. Leon's paper at least claims to deal with the generic things. I have never quite understood it. There are certain things looked as though I get an infinity. I don't know how to handle that. So I'll let Leon answer the generic things.
In any case, we're writing a formula which kind of localizes the eigenvalues. You know that.
Correct. I know, but I can't explain it. But you can explain
Yeah, I can
it.
explain it to you, but you can run it on a computer. Our formula.
Yes.
You can run it and see what happens. I don't know. I've never run it.
All right.
Because the gauge theory we also talked about use an operator which we identify here.
Not operator, actually diagonalized one already.
Use an operator which we call field.
Wait. If it's diagonalized, it's essentially you're doing a scalar TQ equation. It's an eigenvalue equation, right? Yeah. So you don't have eigenvector information.
Well, it's an operator acting in the space of states of gauge theory.
But remember that the distinction between odd and even number size has been swept under the rug, right?
Oh. So the question is what would be the odd even question for the gauge?
For us, we can only do the even number of sides actually. Something back happens when the number of sides is even. Is off actually.
Right.
Why do you think that?
Because the theory is anomalous.
Oh.
Yeah, and let me make a comment about that. In some sense, that's the most curious case of all, because if n is odd, and you're in one of these cases where the Q matrix exists, then you don't have any degeneracies, in fact. But the only degeneracy which exists is the order 2 degeneracy of flipping the whole thing over. But if you're in this curious case where I don't have a Q matrix, then there are some solutions which have a string property. But most of the solutions don't. So you mix the two cases together. There's something very curious in the case that corresponds to the importance of being off. And I don't know what the answer to that is.
The information of the language actually is there is a execution of anomaly free, which probably can be traced to this. So final answer is well, the theta, theta term is one of those already, right? In a sense, because you need to change theta. Well, Bajanov actually, I don't know. He already told. No, Bajanov told me that he discovered it himself last year.
Okay, let's